welcome to Easy BTech, your guide for BTech and beyond. In this channel, you can learn the subject very easily. This is Sampath. I am going to explain the subject VLSI. Last class we discussed about NMOS fabrication. There are 9 following steps are there. CMOS also following the same 9 following steps. Only changes in substrate area and in the diffusion area. N-type substrate area used and source and drain are P diffusions. Let us see. Today we discuss CMOS. CMOS is complementary metal oxide semiconductor. It's a complementary metal oxide semiconductor. First we will see the introduction about CMOS. Then we will see the different ways of CMOS fabrication. So CMOS, in this CMOS, both transistors both transistors NMOS and PMOS in a circuit. So both transistors are in a circuit. You see, so NMOS and PMOS are complement each other. NMOS is a basic transistor. NMOS is basic transistor. NMOS is basic transistor. PMOS is complement of NMOS. So both are in a circuit is called. So NMOS is a basic transistor. PMOS is a complement of NMOS. Both are in circuit called CMOS. This is a CMOS definition. CMOS is designed by both transistors, NMOS and PMOS. PMOS is a complement of NMOS transistor. NMOS is a basic transistor that we discussed last class. There are 9 following steps are there in designing process. And PMOS is also the same 9 following steps, only substrate area and P diffusion area is different. So remaining will be same. Follow as per the diffusion and the changed diffusion and the substrate area, N-type substrate area. CMOS is a dominant. CMOS is dominant over NMOS transistor. So NMOS is a basic technology, but CMOS is a dominant technology, dominant over NMOS in power based. So it is a low power design. It is a low power and high performance in IC technology. By using CMOS, low power and high performance, high performance performance in IC applications. So in IC applications, in IC design, so basic NMOS transistor, CMOS is a dominant than NMOS. So in power, low power and high performance in IC applications. IC applications. So this is about introduction about CMOS technology. Okay, let us see the how can you design CMOS. How can you design CMOS? All these are MOS transistors. You see, MOS. C is a complementary. MOS is a metal oxide semiconductor. So CMOS design is a three ways we can design. Three ways we can design. Any way we can design. First one is a P well design. Second one is a N well design. This is mostly used well design. Now third one is a twin tub, means two wells diffused into the substrate area. So CMOS can be designed by the three ways. First one is a P well, second one is a N well, and twin tub. So it is a so in the subject it is given by the well processed CMOS design. So well processed designs are P well, N well, twin tub. So mostly used N well. Let us see the first one, CMOS, CMOS, P well, CMOS, P well, CMOS, P well process, CMOS, P well process, design process. You see the following steps are there as like in NMOS fabrication. So basic design process NMOS is the so that can be followed in CMOS process. The first step you can take P well diffusion, P well diffusion, P well diffusion into N type substrate area, N type substrate area. So whatever I've discussed diagrams, you can neatly diagram in external exam. So CMOS, the basic different types. So any type will be given in exam. So you can follow diagrams neatly and explain as per the diagram. So P well diffusion into the N type substrate area. First we can take N type substrate area. How we will get N type substrate area? In NMOS fabrication, take a silicon wafer, add N-type impurities. N-type impurities means mostly used phosphorus, phosphorus impurities. Okay. Now this is a N-type substrate area. Then above is SiO2 layer. Above is SiO2 layer. Then here we can diffuse P well. You see, this is the P well. So in a layer representation, let us see this one. First one is N-type substrate area. Okay. So forward, backward slashes representation. N-type. Silicon with phosphorus impurity dopants added. Then it is a N-type substrate area. So then after SiO2 layer formation. You see this one. This is a SiO2 layer formation. It is protect to this P-type substrate area and barrier for the next higher layer. Okay, then P well diffusion. P well diffusion. So P well is P type substrate area. Like it is act as a substrate area for another transistor. You see here, this is a N type substrate area. This substrate area is for PMOS and diffuse substrate area for NMOS transistor. So both substrate areas are for two transistor formation. So in this P-type substrate area, we form NMOS transistor. This N-type substrate area, we can form PMOS transistor. So the first one is, this is a P-well diffusion. P-well diffusion. Right? This is the first process. Let us see the second one. The second one, active area, active area and gate oxidation, gate oxidation, active area and gate oxidation. Active area is for two transistors, active area. So how many transistors are used in these two transistors, PMOS and NMOS? So for that we use two active areas and gate oxidation for two transistors. Gate oxidation. So thin oxide and polysilicon. Let us see, ma. Let us see this. So it is a substrate area and two active areas here, two active areas, and then this is a thin oxide. This is a thin oxide. You see this one more. This is a thin oxide and polysilicon and polysilicon. So as per the layers, and we already diffused P well over here. This is a P well. So as per the layers, we can take this N-type substrate area. First we are taken N-type substrate area. Then after this is SiO2 layer. This is SiO2 layer. SiO2 layer. Dotted lines. SiO2 layer. Then we diffused P-type over here. P-type well diffused into this N-type. So N-type is a parent substrate area. P-well is a child substrate area. So child substrate area diffused into the parent substrate area. So parent substrate area act as a substrate area for, this is a PMOS, and child substrate area P well diffusion act as a substrate area for NMOS transistor. So after this, this is a, you see, this is a polysilicon formation. So this is called polysilicon for gate terminals. Polysilicon, and this is one polysilicon, this is one polysilicon. So two polysilicons for two transistors, NMOS and PMOS. And this is a thin oxide, thin oxide. You see, gate oxidation. Both are called gate oxidation. Polysilicon below thin oxide is called gate oxidation. Active area and gate oxidation. Next we can see The third one, P plus diffusion. P plus diffusion. P plus diffusion for source and drain terminal. Source and drain terminal. So it is for a PMOS. It is for PMOS. It is for PMOS. Now let us see the diagram. The design P plus diffusion. So basic, first we are taken n-type substrate area. Okay. Then this active window formation, two active window formation, and here we diffused P well. It is a P well. Then thin oxide and polysilicon, thin oxide, polysilicon, gate oxidation also we call. Now by applying mask, here we are applying mask and we diffuse P plus diffusion. We diffuse P plus diffusion over here. This part we can diffuse here now. Here we can diffuse P plus by heating this substrate area with high degree temperature. So this area we can dopants, p-type dopants, boron dopants diffused into the substrate area. So as per these layers, we can see this is a n-type substrate area, parental substrate area. Then we are taken SiO2 layer. This is thin oxide. This is thick oxide, thin oxide, thick oxide. So after this polysilicon formation act as a gate and we diffuse it. This is a p-type well diffusion, p-type well diffusion, and here P plus diffusion. P plus diffusion, it is a forward lines with a distance. The representation, it is a representation. It's a layer representation. So this representation is called so different layers with different representations. So forward lines with distance, it is a P plus diffusion. So this is a P plus diffusion by applying mask. So this is a closed area. So this is a closed area and this is an open area. Through this open area, this is an open area, we can diffuse P plus diffusion dopants into the substrate area. So it is a P plus diffusion. P plus diffusion. So this is the third step. So you see P plus diffusion. You see here. So polysilicon and thin oxide. So it is a gate. So this is a gate terminal. This is a gate terminal and the source drain. Source drain P plus diffusion. Source is formed. Drain is formed. So this is a PMOS transistor is formed. PMOS transistor is formed. So last class we are seeing NMOS fabrication. So in PMOS fabrication, you see this one. Substrate area is N-type substrate area. Source drain are P plus diffusion. So polysilicon is same as in NMOS and here also same. Polysilicon and thin oxide. The next step we can see already PMOS is formed. Now here we can diffuse N plus diffusion. N plus diffusion for NMOS transistor formation. N plus diffusion. N plus diffusion for source and Drain terminals. Source and drain. Source and drain terminals. Source and drain terminals. So this is a NMOS transistor. This is a NMOS transistor. NMOS transistor. NMOS transistor. Let us see the diagram. Let us see the diagram. You see this one. So the bottom area is N-type substrate area and active window SiO2 layer. Then we diffused here P well. This is a P well. Afterwards, thin oxide and polysilicon for gate formation. Thin oxide 0.1 micrometer, polysilicon as a gate terminal. So polysilicon is nothing but it's a multiples of silicon elements. So olden days it is a metal, but nowadays modern days so replaced with that metal as a gate. Now polysilicon as a gate for good conduction, protected by temperature, not affect in the conductivity. Because this source and drain substrate area, when source and drain diffusion here, we can heat the substrate area with high degree temperature. So it may be melt if you are using gate as a metal. That's why we can use polysilicon for good conduction, not affected by temperature. So just now we diffused here P plus diffusion. P plus diffusion. Here we are applying mask above. Here we are applying mask. Here we are applying mask. Here we can diffuse this area, this exposed area. We can diffuse N plus diffusion. N plus diffusion. Okay, you can take a N plus diffusion over here for N mass terminals. So let us see the layers representation. So this is a N type substrate area, backward forward slashes. Okay, then we can see the SiO2 layer. SiO2 layer. You see, this is a thin oxide, thick oxide. This is a thick oxide. Dotted lines. This is a thin oxide below the polysilicon. Act as a dielectric layer. This is a thick oxide, and we diffused this P well. This is a P well, ma. You see, this is the P well. So then after gate terminal formation, polysilicon act as a gate, act as a gate, and we diffuse this P plus diffusion. So forward lines with the distance, forward lines with the distance. Now with the mask, we diffused N plus diffusion, N plus diffusion, forward lines with a nearer distance, forward lines nearer distance. So it is a N plus diffusion, N plus dopants diffused into the substrate. What are the N plus dopants? Phosphorus dopants are used to diffuse into the substrate area. So act as a source and drain terminals. Act as a source and drain terminals. So N plus diffusion. N plus diffusion. So here also you see how many terminals are formed here. Polysilicon and thin oxide is a gate, and this is a source terminal, and this one is a drain terminal. You see this one, ma? You see this one? So this is a NMOS transistor is formation, and previously N plus diffusion, PMOS is formed. So both transistors are formed. So both transistors are formed. So that is called as CMOS. Now let us see the fifth step. After this, The fifth step, contact cut. We can take contact cut, for gate, source, drain, terminals. So required area will be taken. So gate, source, drain, terminals. Only required area is taken. Only required area taken. Required area taken. Remaining area closed with SiO2 layer. Remaining closed with SiO2 layer, as you can see in NMOS fabrication. Eighth step. The sixth one, after contact cut, we can take the metallization. So metallization for external contact leads. Metallization for metallization for contact leads. So after the leads taken, then seventh step, over glass except metal leads. Over glass placed. Over glass placed. Over glass placed except metal lead. Except metal leads. So remaining area covered with glass for bonding pads. Bonding pads. Ceramic material is covered top and bottom. Encapsulation. Bonding pads. So then it is a CMOS P-well. So CMOS is designed by using a P-well. Now second one, we can see the process CMOS N-well process, mostly used process, CMOS N-well process. CMOS N-well process. Let us see the flow chart. The diagrams are different. Means interchanging the substrate area and well diffusion. That is changes in CMOS N-well process. Interchanging substrate area and well diffusion and source drain, PMOS, source drain, NMOS, interchanging when in the diagrams. Okay, so let us see this one. The first step we will see here. So first one is N-well diffusion. N-well diffusion into. So what is the substrate area? Opposite substrate area, P-type substrate area. P-type substrate area. That is first one, N-well diffusion. Second one, active area. Active area and gate oxidation. Gate oxidation. So here, N-well diffusion. What is the parental substrate area? Parental substrate area is B-type substrate area. Parental is B-type substrate area. Diffused or child substrate area is N-well diffusion. Now third one, you can say P plus diffusion. P plus diffusion into N-well. So P plus diffusion into N-well for source and drain terminals. Source and drain terminals. The fourth step, by using mask processing, N plus diffusion. N plus diffusion. N plus diffusion into P-type substrate area. N plus diffusion into P type parental substrate area. P type substrate for source and drain terminal. The fifth step. So it is source and drain PMOS is formed, NMOS is formed. Then contact cut, contact cut for gate, source, drain terminals. Required area is taken. Terminals. Then sixth one, metallization. Then metal area for contact leads. Metallization for contact leads. Contact, contact leads. Then seventh one, same over glass. Over glass is placed for over glass for bonding pads. Bonding pads. So this is a process for a CMOS N-well. Let us see the diagram for a CMOS P-well, CMOS P-well inverter, V in, V out, VSS and VDD connections. VDD connections. Let us see this in the design connections. Let us see the design connections. So first we can take a substrate area. P-well means N-type substrate area. P-well means N-type substrate area. Diffusion is P-well. Diffusion is P-well. You see, this is active area for two transistors, two active windows for two transistor formation. So here, first we diffused P-well. First we diffused P-well. Then thin oxide. You see, this is a thin oxide and polysilicon. This is a thin oxide and polysilicon. And we diffused here. N-type means P plus diffusion here. This is a P plus diffusion. And this one is N plus diffusion. Okay. Let us see the layer representation. So first one here is backward forward slashes N-type substrate area. N-type substrate area. Silicon with the phosphorus impurity dopants added. Okay. Then after you can see SiO2 layer. This is a thin oxide SiO2 layer. SiO2 layer. It is a protection for the substrate dopants. SiO2 layer. This is a thin oxide. So after this, we diffused P-well here. P-well. P-well. Then you can see this one is a polysilicon for gate terminal. Polysilicon for gate terminal. And so P plus diffusion. Forward lines with the distance. Then here N plus diffusion. Forward lines with the nearer distance. Now we can say the connections. We can take the connections. So from here to here, V in. This is V in. And this is V out. Designing part is connected. Design. So two transistors are formed. Now we can take the connections. Okay, from here to here and here to here. So let us see the first one. This is V in. This is the input terminal. This is output terminal, and this is a ground terminal, and this is a drain terminal, VDD. So it's a design part. Let us see in a circuit representation. Let us see in a circuit representation. This is a circuit map. CMOS inverter. So both transistors are in series, NMOS and PMOS. So whether the input and output and supply and ground connected or connected is correct or not, we can check by this circuit. So this is V in. Then input is applied to the gate terminals, the supply voltage VDD, and the ground terminal VSS, and output voltage is in between the source and drain terminals. You can see this one. You can see, so it is a above is PMOS, below is NMOS, so seriously connected. So PMOS is complement of NMOS. PMOS is complement of NMOS. So logic 0 is applied on logic 0, PMOS is on, logic 1, NMOS is on. You can see this is a gate terminal and this is a drain terminal and source terminal. Gate, drain and source terminal. So both inputs are given to the polysilicon gate terminal. So both inputs are given to the polysilicon. This is a V in terminal. Okay. Now output is taken, drain of source. Output is taken. So this is a drain. So drain of PMOS and drain of this NMOS. So both layers are connected here. So drain of one drain VDD. One drain is a PMOS drain, another drain is a NMOS drain. Okay. Now, so this VSS means it's a ground connection. What is 1S and second S? 1S is a source of 1S is the majorly source. This is a source of here. This is a source of NMOS and the source of PMOS. The source of PMOS. So it is a drain terminal. So V out. Now V out means drain of NMOS and source of PMOS. This is output terminal. You can cross check with this. Okay. So it is a CMOS P-well inverter, input output VSS VDD connections. CMOS N-well also, if it is a N-well, so substrate area is reverse. You can interchange the substrate area to well and the substrate area into this well into substrate area, interchanging. So interchanging the source and drain terminals to here and interchanging source and drain terminal to here. Then it will be a CMOS N-well inverter. Okay. So let us see the last one. Designing of CMOS. CMOS twin tub. CMOS twin tub process. So let us see this one. The twin tub process, two wells are diffused into the substrate area. Two wells, N well and P well, into the substrate area. So we can take, this is a active window. This is active window. Here one more layer is placed, that is called epitaxial layer. It's a lower conducting path. After this thin oxide, you can see this one. Thin oxide and polysilicon. Thin oxide, polysilicon, one more transistor is formed here. Now we can take any well here. Let us take, this is a P well and this is a N well. Two wells, twin means two. So two wells are diffusion here. So now let us take this layers, the designing part, so that we can understand. So which type of layer it is, substrate or it is a diffusion. So backward forward slashes, it is a n-type substrate area. N-type substrate area. It is a sleeping line. it is called epitaxial layer. Lower conducting path is placed over here. It is a epitaxial layer. So this is called epitaxial layer. Epitaxial layer. Above is placed on this n-type substrate area. Now we have diffusion over here. Let us take the diffusion part. Now this is the diffusion part here. Source and drain terminal formation. Source and drain terminal formation. You can say now which one, by representation of layer you can tell me which type of MOS transistor will be formed over there. Now let us take, this is a p-type substrate area, p well diffusion. So p well diffusion and a substrate area. So which transistor is formed here? Source and drain NMOS. Okay, so it is a p well. Now it is n well. Backward forward slashes. Backward forward slashes. This is a n well. Now here p well means n diffusion. P well means n plus diffusion. Now here n well means p plus diffusion. So forward lines with the distance. Now this is SiO2 layer. SiO2 layer, thin oxide. This is thin oxide. This is thick oxide. Thick oxide, thin oxide, thin oxide. The final is a polysilicon formation. This is a polysilicon formation. Polysilicon formation. You see, this is a gate terminal. This is a gate terminal. Gate terminal formation, and we can see the representation over here. And let us see the connections. So two polysilicons are same. Input is applied to the gate, and also output is taken, one terminal of PMOS, one terminal of NMOS. And here, so always it is a end diffusion terminal. So it is connected to ground. So P diffusion, it is always top layer which is connected to the VDD. So let us write this representation. This is a V in and V out. This is a ground terminal and this is a VDD, supply voltage. So one D is drain of NMOS, another D is drain of PMOS. S is one terminal of NMOS, one terminal of PMOS. So let us see this representation. You can also cross check with this, whether input and output, ground and supply, output voltage, whether connected or not. The common input is applied between NMOS and PMOS. So this is the input terminal. So input terminal common is applied to the CMOS. Output is taken in between drain of NMOS, source of PMOS. This is a ground connection, and this is a supply voltage VDD. So drain of PMOS, drain of NMOS. Output terminal is in between. So one is a source of PMOS, drain of NMOS. In between it is connected to output. So you can also write the terminals over here. So output is a source PMOS. So this is a source and this is a drain. Okay, this is a source and this is a drain terminal. Okay, so one terminal of drain of PMOS, one terminal of NMOS. So one terminal of source, one terminal of source of PMOS, source of this is PMOS, this is NMOS. So these are the three ways we can design CMOS fabrication. So please subscribe our channel and like and share to your friends. Thank you.